Lesson 2.8 is understand the y-intercept of a line. We've been talking a lot about proportional relationships. In this lesson, we're going to be talking about what happens if something's not proportional. So, it says 8-year-old Alex is learning to ride a horse. The trainer says a horse ages 5 years for every 2 human years. The horse is now 50 years old in human years. How can you determine the age of the horse in human years when Alex was born? So, what we want to think about on this, we can think about the different ages. So we're looking at Alex's age and the horse's age. So if we look at this now, we can easily see by the cake that the horse is 50. And it says the very first part in the problem, it says 8-year-old Alex. So Alex is 8 and the horse is 50. We're going to want to figure out age of the horse in human years when Alex was born. And a key to doing this we have to think about is that the horse is aging 5 years for every 2 human years. So 2 human years is 5 horse years. So if we take off 2 years for Alex, she would be 6. That would make the horse 45. And we can do that again. 2 years off for Alex, she would be 4. 5 years off for the horse would be 40. 2 years off for Alex would make her 2. 5 years off for the horse would make the horse 35. And then 2 years off for Alex would be 0, which would be when she was born. 5 years off for the horse would be 30. So we can see that the horse was 30 there when in human years when Alex was born. And this, like I said, is going to be something we're going to be dealing with. We have this point 030, whereas almost all the problems we've been working with, we've been going through the point 00. So this point 030 we'll talk about, but that's actually what's called the y-intercept. There's other ways that we could have come up with the answer to this. One other option would be kind of like what we mentioned before. We could start out with this point 850. And then basically we could think about the horse goes down 5 and then Alex's age goes down 2. So that's like -5 over -2, which is the same as 5 over 2. Since we're trying to work backwards, though, we don't want to go up 5 and over 2. We actually want to go down 5 and to the left 2. So it's a little bit complicated maybe to think about, but down 5 and to the left 2, and then that would take us to this point 645 like we had here, and then we can just keep doing that. Okay, and it's technically a positive slope, but we're kind of working backwards, so that would eventually get us to that point 030. Example 1, Mathilde and her friend are going bowling. She can rent shoes at the bowling alley or use her mother's old bowling shoes. How can she determine how much money she will save if she brings her mother's old bowling shoes? So, if we look at the information they've given us here, usually this is not how it would work actually. Usually at the bowling alley, they would have separate price for your shoes and for your games. But anyway, that's not what they've done here, just to make things interesting for us. The bowling price here includes the shoe rental, and we're going to ask them to potentially, take out the cost for the shoe rental, which sometimes we're just not allowed to do. Kind of like if you go to a restaurant, it says it includes a soft drink and you just want a water, you don't really have the option of saying, can I just get a water and take off the price of that, and I'll, get that kind of a deal. So one game with shoes is $4, 3 games is $8, 5 is $12, and 10 is $22. So one thing we could do here would be to make those kind of as ordered pairs. So like one game was $4, we could make that the 0.14, where X is the number of games and Y is our costs, total costs. I don't like the triangles underneath here, but then we have another 0.38, another 0.512, another 0.1022. And what we can do, kind of like the book's doing, only if we go above this, we can look at our slope of this line. The slope of the line, it's our rate of change, which is going to tell us the cost per game. If we know the cost per game, then we can figure out how much the shoes cost into that price. So if we went from 1.4 to 3.8, change in Y over change in X, our Y value went from 4 to 8, so it went up by 4. Our X value went from 1 to 3, so it went up by 2. And if we do 4 divided by 2, that's $2 per game. We actually only have to do that once because the slope is constant. It's the same for any 2 points. So you can pick another couple points here if you want. The book went ahead and used 3.8 and 5.12. They found out the slope was 2. They used 5.12 and 10.22. Guess what? The slope was 2. All right, you only have to do it once because the slope's the same anywhere. So pick 2 points, find the slope. That's telling you it's $2 per game. So if it was $2 per game, but one game costs $4, that means it's $2 for the game, and it's $2 for the shoe rental. And you could actually work that out with all these other points as well. And you'll see $2 is the shoe rental cost. The rest is the game cost. So for example, 3 games was $8. Well, $2 a game. So $2 a game, 3 games, that's $6. And then plus our $2 shoe rental makes $8. So if we can convince them to take out the $2 shoe rental costs and give us a little bit of a break on the price is kind of what we're asking for here, basically. Another way we could do this, besides working it out there, would be to extend our graph. If we graph it through those points, and if we can draw a perfect line, and if the point comes out exactly perfectly, we could maybe tell that that's hitting at the point 0.2. So 0.2 seems like a point that doesn't really make sense because 0 is our X, so that's telling me 0 games. 2 is my Y, which is my cost. So 0 games cost $2. That doesn't seem like that makes any sense. We didn't even play and it cost $2. Well, that's that y-intercept that we'll talk about, and that's then the cost of the bowling shoes. So we could technically, if they'll let us break our price down, technically rent shoes for $2, not play any games, and just be done with our $2. Really no sense in doing that, but that's kind of, again, that point doesn't, in reality make a whole lot of sense maybe, but that's kind of, it's an initial cost, basically, is what that amounts to. So on the try it, we have a similar situation. Prices for a different bowling alley are shown in the graph. How much does this bowling alley charge for shoe rental? And this one, if we just cut to the chase here, the book says the line crosses the y-axis. It should be at. Crosses the y-axis at. And again, we're going to depend on this being an exact easy point for us to tell what it is. It's really not the easiest point for us to tell what it is, but here it is hitting the y-axis. That point would be 2, so this would be the point 0, 3 it looks like. Again, not always going to be an exact point, so this is probably not the most reliable way for us to tell the answer to this, but really none of the points they gave us except for the last one, the 10, 18, that's really the only point that comes out very nicely there. So it crosses the y-axis at 0, 3, and then from that, that's our y-intercept. When we say what the y-intercept is, the x is always 0. So x is 0, y is 3. We can just say then the y-intercept is 3. Okay, y-intercept is 3, which again basically tells us that's an initial fee, initial charge. So that's basically telling us it's going to cost $3 for shoe rental, and then after that, then we pay so much per game. Example 2, a robotic assembly line manufactures a set number of parts per minute. Use a graph to verify how many parts the assembly line manufactures when it is first turned on. So step 1, it says predict, so it hasn't made any parts when it's first turned on, so the answer should be 0. So we're determining at different points here. You can see here from this information it's making 12 parts in 1 minute, so 12 parts per minute. 12 parts in 1 minute. I would have gone ahead and said 24 parts in 2 minutes. The book skipped ahead, that's okay. 36 parts in 3 minutes. And really, once you get 3 points, that's really enough at that point to tell what it's doing. And when you graph those points, the graph goes through 0, 0. And so that goes with what our initial prediction is. It goes through 0, 0. So y-intercept is 0. And so no parts were manufactured when the line is first turned on. Again, kind of a little bit of a common sense on that one maybe. But again, understand the y-intercept can be 0. If it's proportional, your y-intercept will be 0. Example 3 just asks what is the y-intercept for each of the relationships shown. So it's basically just a matter of understanding what a y-intercept is. Y-intercept is telling us where does the graph intercept the y-axis, basically. Okay? So this point is 0, 2. The y value where it crosses the y-axis is our y-intercept. So y-intercept is 2. The second one here, where does it hit the y-axis? Well, it's hitting at the point 0, -1. So our y-intercept is -1. And the last one actually is going through the origin, point 0, 0. So that's hitting the y-axis at 0, so y-intercept is 0. So if we look at the try it, again asking what the y-intercepts are of these graphs. So for the first graph, it's hitting at the point 0, 2. And so our y-intercept is 2. And if we look at the second one, our second graph is hitting at 0, negative 0 and 5/10, so our y-intercept would be negative 0 and 5/10. So basically, if we know what y-intercept means, then should be in good shape with these problems.